Hello, AP Chemers. Today we are going to start chapters 6 and 7. So 6 and 7 talk about the periodic table in general, so electron configurations, periodic trends, things like that. So these are the learning objectives as always. A couple of exclusion statements here. You do not need to know the exceptions to the Aufbau principle, and we'll talk more about that. But if you remember last year when we were doing electron configurations, things like the copper family and the chromium family had exceptions, so no need to worry about those this year. Also, you don't need to worry about quantum numbers for this year. We're going to go over the notes. We're also going to do a lab that's really important that shows up all the time on the AP exam. So I put a little box for you here at the beginning of the study guide telling you don't forget to review this lab and Beer's Law. Okay, so we're going to start chapter 6 with atomic structure. And we know that de Broglie said that electrons have a dual nature, right? They behave both like particles, and so they have mass and volume, and they also behave like waves, so they behave like energy. And so what else comes in waves? Well, light comes in waves, and so the study of light really led us to some different discoveries in the atomic structure, because just like electrons, light is waves. So let's look at some waves here, and this should be review from last year, also from physical science. You've studied waves, and some of you maybe are even in physics. We're going to start with wavelength. So the symbol for wavelength is lambda, the Greek letter that sounds like an L, but it looks like an inverted Y, and it is the distance between identical points on successive waves. So either from crest to crest, or trough to trough. That would be the wavelength. Since it's a length, it's measured in units of length, so you probably want to use units of meters or nanometers or any really unit of length. Typically we use meters since that's the base, or nanometers because they're so small, because light waves are very small. Next is frequency, and frequency gets the Greek letter nu, so the Greek letter that sounds like an N, but it looks like a fancy V, so nu, N-U. And that is the number of waves that pass through a particular point in 1 second, and the units for that is hertz or per second. So the units are either hertz, for short, that's Hz, or 1/seconds, or seconds to the -1. That means 1/seconds. I prefer to use 1/seconds because that makes the most sense to me when I'm crossing out my units, but you can use any of those. So let's take a look at these two waves here. Let's call this wave A, and let's call this wave B. So if you look at the wavelength for A compared to the wavelength for wave B, you'll notice that the wavelength of A is much longer than the wavelength of B. So I'm going to say this is bigger, this is smaller. Now look at the frequency. So if this was happening, if they had the same speed, which it's the speed of light, right, for all light waves, this wave B, happens a lot more frequent than wave A. So when it comes to frequency, this one has a much higher frequency, this one has a lower frequency, right? The longer the wave, the less frequent it will be in a given amount of time. The shorter the wavelength, the more frequent it's going to be in a given amount of time. So wavelength and frequency are inversely related, and they are related by the speed of light. So there's the equation that we need to know. C is equal to lambda nu. So lambda, we said, was the wavelength in meters. Nu was the frequency in per second. And then c would be the speed of light, and it is 3 × 10⁸ meters per second. This number is given to you on your green sheets, on your reference sheets to use on the exam. This equation is also given to you, so all you need to be able to do is plug and chug. Just be cautious though, when you use this speed of light, it's in meters per second, so again the wavelength, in here should be in meters, not nanometers. A lot of times I'll give it to you in nanometers, you just have to convert. Okay, so this is an inverse relationship, so as the wavelength increases, the frequency decreases, and vice versa. A lot of times on the AP exam, they want to ask qualitative questions as opposed to quantitative. So they'll ask you, this wave has a higher frequency. Tell me about its wavelength. And so it would have a lower or a shorter wavelength. Okay, the second equation that you need to know about is E is equal to h nu. Again, this is on your green sheet. E is energy measured in joules. H is Planck's constant. So Planck and Hertz were both physicists, and they wanted to honor them, so they named these units after them, or this constant after them. And then nu is the frequency again. Planck's constant is given to you here, and it's also going to be on the green sheet, your reference sheet, 6.626 times 10 to the negative 34th joules times second. Remember that we're talking about light waves here. So in terms of numbers, numerical answers, if I'm solving for lambda, for the wavelength, it should be a very, very small length, right? Usually nanometers. So like 10 to the negative 7th or negative 9th meters. Very, very small, because it's a wet light wave, right? So it shouldn't have very high wavelength. In terms of frequency, that should be a really big number, usually close to 10 to the 14th or so in magnitude, because again, this is a light wave, so it's going to happen very, very frequently because it's very, very fast. And then in terms of energy, that's a light wave, and so your answer in joules here will be very, very small, typically in 10 to the negative 19th magnitude. So negative 19th is very, very small. A joule itself, by itself, is very small, so a negative 19th of a joule is extremely, extremely small, which makes sense because, again, these are light waves. We have light on all the time. It doesn't like knock us off from the energy or anything like that. So the wavelength and the energy are going to be really small. The frequency are going to be really big. So when you look at your answers, make sure that they make sense. All right, so we know that all light consists of electromagnetic radiation, and the electromagnetic spectrum is really big. Depending on the value of the wavelength and the frequency, that radiation or that light will be at a different part of the spectrum. So you can see here, this is the wavelength in meters, and so the wavelength is increasing that way, right? This is increasing wavelength, which means that it's going to be decreasing frequency. The increase in frequency would be that way. Increase in frequency. Remember, we said that they're inversely related. When it comes to energy and wavelength, or sorry, energy and frequency, they are directly related. So the increase in frequency is this way, the increase in energy is this way also. Think about like, just as a visual, if you were in the ocean and standing and you have a wave that looks like this versus a wave that looks like this, which one would you not want to hit you? Probably the one that has a higher frequency like that, because that would have a lot more energy. So the higher the frequency, the higher the energy. So again, going this way, we're increasing in wavelength. Going the opposite way, we're increasing in energy and also in frequency. So we have all kinds of waves here. We have gamma rays, X-rays, ultraviolet, infrared, and in between the ultraviolet and infrared, this small portion, that is your visible spectrum, the Roy G. Biv. And then microwaves, radio waves, and so on. So in my Roy G. Biv, the red has the longest wavelength, lowest frequency, and lowest energy. The violet has the shortest wavelength, the highest frequency, and highest energy. And that's something you kind of need to know. So if I tell you, hey, I have an orange light and a green light, which one has a higher frequency? You should know that it's the green. Which one has higher energy? It's the green. Which one has a longer wavelength? That would be the orange. So you need to be able to qualitatively tell that. Okay, so let's try a problem here. It says a light source emits electromagnetic radiation at a frequency of 4.84 times 10 to the 14th hertz. So hertz, that tells us this is the frequency. So this is my frequency. And it makes sense that my number is really big because light wave would have a very high frequency. It says calculate the wavelength and the energy of the emitted photons and what is the color of the light. So I need to find the wavelength and I need to find the energy. And then I also need to figure out what color it is. So let's start with the wavelength. So I need to find an equation that links between the wavelength and frequency. And so that would be C equals lambda nu. I know that my C is 3.00 times 10 to the 8th meters per second. That's the speed of light, is equal to lambda, which is what I'm solving for. And then my frequency is 4.84 times 10 to the 14th. And it says hertz. I prefer to write 1 over second because then I can tell that this is 1 over second on this side, 1 over second on that side. Those are going to cancel. And I know that I would end up with units of meters at the end. So I would take this number divided by this number to solve for the wavelength. And it ends up being 6.20 times 10 to the negative 7th meters. Again, I end up with meters here. If I wanted to change it to nanometers, which it doesn't ask me, but sometimes it might ask to report in a certain number, you do need to know the conversion between meters and nanometers. So 1 meter is 10 to the 9th nanometers. Nano 9. So this would be 620 nanometers. Again, you don't have to report it in nanometers, but just so you know the conversion. Okay, we also need the energy, so I can use E equals H nu. E is what I'm solving for. H is 6.626 times 10 to the negative 34 joules times second. That's Planck's constant. My frequency is 4.84 times 10 to the 14. And then I like to use 1 over second because they're both on the same side. One is in the numerator, one is the denominator, so I can cross those out, and I know that I end up with joules. So my energy ends up being 3.20 times 10 to the negative 19 joules. All right, last thing they ask about is the color of the light, and unless they give you more information, like something like this, or some numbers, you wouldn't know. Back in the day, before 2014, you had to memorize what the wavelength of each color was, but not really anymore. Just so you know, just for fun, the way that we do it, Roy G. Biv, just to estimate, basically we know that the red has the longest wavelength, right? And violet has the shortest wavelength. The range in the visible spectrum is about 400 nanometers to 700 nanometers. And so it's not exact, but each color is about 50 off. So this would be like 450. This is 500, 550, 600, 650, and then 700. So again, it's an estimate. You do not need to memorize this. This is just FYI. Again, if they ask you about the color, they'd have to give you more information. All you need to know is that this side of the spectrum has the longest wavelength, and this has the shortest. So 620 would probably be somewhere here, so like a yellow-orange color is the color of this light.